Hello everyone. In this video we will continue to examine topic 1.2, uncertainties and errors, and in particular we will begin to focus in on error bars and uncertainty of gradient and intercepts. Alright, so often we will combine multiple measurements in a graph and we'll propagate the uncertainties on graphical quantities, so the gradient and the y-intercept, using the graph. Now, this is something we'll spend a lot more time on when we first do a lab and we process the data. So I'm going to introduce it in general here, but I don't want you to stress about it until we hit the lab, at which point it might be a good idea to come back and take another look at this material. The idea is, let's say that we have found a relationship between y and x, and that relationship is expected to be linear, as shown here. You'll use a graphing software, either Excel or Desmos or Logger Pro, to find a best fit line. It does a linear regression on those data points and finds the best fit line to those points. And then often what we will end up doing is taking the measured slope or gradient of that line and using it to determine another value. So it's important to be able to sort of measure the gradient and using the error bars, which represent the uncertainties, get an uncertainty on the gradient itself. And the way we do that is by taking that best fit gradient and asking ourselves, all right, what is the highest gradient and the lowest gradient that would be reasonable to fit within the error bars as best we can? If the error bars are perfectly in line with each other, if you have no sort of incidences of mild systematic error, and the relationship is as you expect, the best fit line will go through all the points. Sometimes, though, that doesn't happen, and that's okay. We're just using the collective, all of the data together, to measure that best fit relationship between y and x, that is, the gradient of this line. As a result, we're going to eyeball a max fit gradient line here. Okay, so that is the highest slope that will fit within our uncertainties, as shown on the graph, and eyeball a minimum gradient. That is the lowest slope that will fit within our uncertainties on the graph. Notice that to put these in on Excel or on Desmos is kind of a pain, and we'll get to sort of the practical realities of that a little bit later on. But if you're quizzed or tested on this in an IB question, they literally expect you to take a ruler and draw a maximum best fit line and a minimum best fit line by hand, ideally within the error bars if the error bars are appropriate for that. Then, once you have that maximum gradient and that minimum gradient, you can use the range technique to find the uncertainty on the gradient. That is, you take that maximum gradient, you subtract the minimum gradient, and you divide by 2. And then your value, your measured value for the gradient, is whatever that value is from your graphing software or from what you've calculated by hand, plus or minus the max gradient minus the min gradient divided by 2. And that's your uncertainty on the gradient. Now, sometimes we will also use a graph like this to get our best fit measurement of the y-intercept, because the y-intercept will tell us a physical variable of some sort or another. Notice that in order to do that, you use your best fit line. That best fit line is going to have a y equals mx plus b relationship, and that b right there is your measured y-intercept. And then your maximum y-intercept can be found by using that maximum gradient. So it's the intercept of the maximum gradient. The minimum y-intercept can be found by using the minimum gradient. It's the constant for the minimum gradient. It's that intercept for the minimum gradient. And your measured value of the y-intercept is then y-intercept plus or minus max minus min divided by 2, just as before. Notice we will often use the gradient and the y-intercept to find other sorts of physical variables, and we'll have a lot of practice in our laboratory work doing just that. So again, this is just a short introduction to the kind of processing we'll be doing to propagate uncertainties on a linearized graph, and we will return to this over and over as we undertake the laboratory work in this course.